we're continuing to develop some basic ideas with sequences. So a collection of numbers in a basic way. A sequence is a collection of numbers whose domain is the natural numbers. What are we really doing with most of these? We're just looking at the limit as n goes to infinity. If it converges to a number, the sequence converges. If it goes to infinity, it diverges. And if it just doesn't exist, the limit, like an alternating factor, we may have to dig a little deeper. That's kind of where we're at this point. Okay, let's take a look at these two examples, and then we'll kind of go in reverse and talk about the summary up there for geometric sequences. All right, so suppose we have this sequence of first one, part A. Suppose we have the sequence of 2/3 to the n. All right, so suppose I was to look at this limit as n goes to infinity of 2/3 to the n. So let's think about this for a second as its reciprocal of 1/3 to the n. So suppose I thought of this as 1/3 to the n, which of course 3/2 is like 1.5. So think about what happens if you have a base that's bigger than 1 and you start plugging in really large powers on that base that's bigger than 1. That denominator is going to get bigger and bigger and bigger. So this denominator is going to go to infinity, and then 1 over something going to infinity is going to go to 0. So this limit is going to go to 0. All right. Now suppose we had this limit as n goes to infinity of this 7/5 to the n. So let's think about that one. Well, what is 7/5? So 7/5 is 1 and 2/5. 2/5 is what, 4/10? So let's just think of this right now as it is. It's 1.4 to the n. So again, a base bigger than 1, as I plug in really large powers on that exponent, this is just going to go to infinity. All right, so we're going to go back and kind of fill in. Maybe like a really simple example would be just a sequence. Let's say I had some sequence C sub n here that was just equal to, and this is pretty boring, 1 to the n. 1 to any power for subbing in the natural numbers is just going to be 1. This would just be the sequence of 1, 1, 1, 1, 1, and so on. So that's kind of boring. But if we think about it then, the limit as n would go to infinity of 1 raised to the first, second, third, and fourth power. This limit would just go to 1. All right, so a sequence that's geometric. So when you think about a geometric sequence, we're really thinking about one that has a common ratio. So if you were to write out these terms, it's 2/3, and then it's 2/3 squared, or 4/9, and then it's 2/3 cubed, or 8/27, and so on. And so what makes it geometric is that every term you get a common ratio going from one term to the other. So every time we are multiplying by a factor of 2/3. We're multiplying by a factor of 2/3. So that's the heart of what a geometric sequence is. There is a common ratio, a base being raised to the nth power. So when you think about a geometric sequence up here, this geometric sequence, if we start at r to the first, of course, we would have r, and then we would have r squared, and then we would have r cubed, and so on, so that each time there is this common ratio. And so that's what is a geometric sequence. So each time you go from one term to the other, you are multiplying by another factor of r. So that's a geometric sequence. All right, so these geometric sequences, a base of r, a real number raised to the nth power. So let's think about the last one we just did. If that r is 1, so that's kind of boring, but if that r is 1, then it's going to converge to 1. So it will converge to 1 if that common ratio, if that base is equal to 1. Now it is going to converge to 0, and we're going to extend what we did in part A a little bit, if that is a kind of a fractional value in between like -1 and 1. So what we typically say is if the absolute value of r is less than 1. So something, the other way to say that then is if that ratio is something in between -1 and 1. So something like 2/3. And then it diverges for all other numbers. So something where the common ratio, where its absolute value is bigger than. So in other words, if that absolute value of that common ratio is larger than 1, then it diverges. And of course, we can look at that now with everything that we just saw here. So this one converges, and it converges to 0. And now I can also see, so that was one way to think about it, but now we could say, or we can look at it and say, because it is geometric, where we have the common ratio here of 2/3, and the absolute value of that 2/3, that common ratio, is less than 1. That's another way to know that it converges to 0. We can look at that second one we just did and kind of apply the same logic. So we also could have just said, or once we've cited that it's geometric, we could have said, because this is geometric with, and in this case, that common ratio is that 7/5 or 1.4, and the absolute value of that, so just obviously 7/5, is greater than 1. So this implies that it diverges. And of course, that's what we know if the limit goes to infinity. So these two, go hand in hand. And then of course the last one, it's geometric and the ratio there is 1. So it converges to 1. All right, so geometric is kind of nice. You can just look at the base and then kind of quickly tell. All right, but you can always just go back to the limit too. That's really the heart of this section. All right, now, something else we're going to talk about here is monotonic sequences. So what's a monotonic sequence? In a basic way, we're talking about a sequence that's either increasing or decreasing or equal. So you can have equality. So if we talk about a sequence that is non-decreasing says that a subsequent term is bigger than or equal to a previous term. So you can think of non-decreasing as increasing or equality, right? So kind of just think of this one. Non-decreasing is like it's either increasing or equal. So it doesn't have to be strictly increasing. And a sequence is non-increasing. So non-increasing, you can think of that as really being decreasing or equal. So non-increasing is decreasing or equal. And so when we look at these, that's saying that a subsequent term would be less than or equal to a previous term, whereas the non-decreasing says a subsequent term would be greater than or equal to a previous term. And both of these are what we call monotonic. So you are monotonic if you are either non-increasing or non-decreasing. And there are several different ways to show that a sequence is monotonic. Okay, so let's say we started off here and we thought of, so we're going to have kind of two categories for everything. So we have our non-decreasing category on these, and then we have our non-increasing category. So we have our non-increasing category. And everything we do here has to be true for all n greater than or equal to 0. So when we think about non-increasing, so we're really just thinking about, again, that we start off and a subsequent term would be bigger than or equal to the previous term. So think about what happens if you subtract a sub n over to the right. You would have that a sub n plus 1 minus a sub n is now greater than or equal to 0. So basically, this is saying that this would, if this is positive, of course, or 0, then you have something that is non-decreasing. Okay, over here on the right, again, if I start off with my assumption, that a sub n is greater than or equal to a sub n plus 1, so a subsequent term is less than or equal to a previous term. Again, let's say that you were to subtract the a sub n over to the right-hand side. So now you're saying a subsequent term minus the previous term is now less than or equal to 0. So now this is saying that what you get is negative, again, technically, or 0. So this is one way to show, and this would have to be, so if you were going to use this as a way to show non-increasing or non-decreasing, of course, it has to be true for all n greater than or equal to 1. All right, so what else? How else could we do this? Well, instead of subtracting the a sub n, what happens if we divided by it? So if I divide both sides by a sub n, so let's just kind of think about that, then I would have 1 on the left would be less than or equal to a sub n plus 1 divided by a sub n. So if that ratio is greater than or equal to 1, that would be another way to show that you are non-decreasing, or basically increasing. Okay, over here on the right, again, let's think about if you start with the original just kind of definition and you divide it by a sub n. So if you take the subsequent term divided by the previous term and you get something less than or equal to 1, then that would also show that you are non-increasing. So again, if you can show that to be true, you can do that for all n greater than or equal to 1, you're in business. All right, the last way is just to kind of use Calc 1. So think about with Calc 1, if you were to find the derivative, so if you use the derivative, and for non-decreasing, so basically increasing, if the derivative is greater than 0, okay, then this would tell you that you would be increasing. So if you're increasing, then you're definitely non-decreasing. And over here on the right, if you were to find the derivative, and if you were able to show that it was less than 0, then the derivative is negative, then you are decreasing, and decreasing definitely satisfies being non-increasing. So again, if you are able to show that these things are true for all n greater than or equal to 1, these are 3 different ways that you could show that a sequence is monotonic. So let's look at one example here. So we have 3 over n plus 5. So this is a sub n. So a sub n is equal to 3 over n plus 5. And then the next term, a sub n plus 1, that would be 3 over n plus 1 plus 5. So that's going to be n plus 6. Now, I'll be honest. If you have a bigger denominator, that means the overall fraction is smaller. You should be able to kind of look at this right here, in my opinion, and just simply observe that the bigger denominator certainly means that that subsequent term is going to be less than or equal to the previous term. So, this one's going to be decreasing or non-increasing. But in lieu of that, if we weren't sure, what can we do? Well, we're trying to kind of figure out, let's say, what the inequality would be in here. So one thing we can do then would be to just simply subtract the a sub n term to the other side. So we're going to subtract the 3 over n plus 5 term to the other side. So now what we have on the left-hand side is 0. We're trying to figure out what the inequality would be if on the right-hand side our a sub n plus 1 is 3 over n plus 6 minus our a sub n is 3 over n plus 5. So we're really kind of following more what we see up above in step 1. So we're trying to decide if what we get on the right-hand side is positive or negative here. All right, so let's go ahead and kind of compute this to get a common denominator. You would have 3n plus 15 minus 3n distributing through the negative minus 18, kind of multiplying each one by the other denominator, all over the product of n plus 5 and n plus 6. And so I now have the 3n's go to 0. I have negative 3 over my n plus 6 times n plus 5. Now remember, n, so for all n greater than or equal to 1, it is certainly true that the n plus 6 and the n plus 5, that denominator is positive. So that denominator is positive. And so I have a negative numerator divided by a positive value. So clearly this value is going to be negative. So this whole thing here is definitely going to be less than 0 because it's going to be negative. So when you do the an minus the an minus 1 and you get something that's negative, where in the right-hand column there you have something that's non-increasing or decreasing. Okay, so therefore we are decreasing, or if you want to say it more generally, in this case it's definitely a strict decrease. You can say it more generally as non-increasing, which is fine as well. And so if you have either of those, that of course means that you are monotonic. Again, to me, right away in the very beginning, a bigger denominator means a smaller fraction. So, I mean, I think that you can almost kind of look at it this way and just sort of see in a simple example like this one that you are definitely decreasing. And I don't know that you need that more robust approach, but it's nice to know that it's there for ones that maybe aren't so obvious.